So today we're going to work on more thermodynamics. So today, folks, is almost only going over examples. Okay, I'm going to experiment because I don't know if I was conveying to you what I was trying to convey to you in the first 4 weeks, or whether I was getting it presented okay and you were just not getting it. Okay. And now we're going to go over examples. So all I'm doing right now, folks, is I'm going over, I've got some other stuff in here, but basically, example 8.1, 8.2, 8.3, we're going to do them all. Okay? It shows you how to solve the problems, which is the main thing you need to know. I will try and teach you something about the theory, why things are the way they are. For those of you who are chemistry majors and are going to go on to take physical chemistry, then you will take thermodynamics, and in that class you can learn in more detail how and why things are the way they are. Okay, so, all right, the second law and the third law. So, this is where we stopped. If you were to look at this, would you say that this system right now, with all these molecules over there on one side, has more or less entropy than if it had both sides? So I had somebody last night arguing that that was not the case. Okay, that things are more chaotic here, okay, than they are here. Granted, you pack enough people in a telephone booth, it gets kind of chaotic, but you have less movement. Okay, that's what this is about, is the freedom to move from one side to the other and all around. So if you double the volume, entropy increases. And we have an equation we'll learn about that. So, once again, this will never happen. Okay, you will never have all these balls go over here. Now, let's say we had one ball. Okay, one ball. It can either be on this side or this side. So, if we had only one ball, and it went from this side, this side to this side, then the reverse is possible, right? 50% of the time that one ball is going to be here, and 50% of the time it's going to be there. Okay? What if we have two balls? Okay? Chances are you'll have one on each side. You agree with that? But occasionally, do you think there's going to be a time when you have two balls on one side and none on the other? Sure. With two things and two sides, that's not statistically very difficult. Okay? You see what I'm saying with that? How about if we have three? Less chance that you're going to have all three on one side than the other, but three is still a workable number. But not this many balls. The bigger you get, the less possible, the more impossible it is that you're going to get all of these crammed over here. It's the same thing, folks, as in this room. Okay? There's nothing stopping every molecule in this room from going over there to that corner. Nothing. But it's not going to happen, because as many molecules are going that way as are going this way and so on. If, however, we had one molecule in this room, then it could be just as easily over there in the corner as it is in this corner. Okay? So once again, having this extra volume increases entropy. The reverse never happens when you have this many. So this was an equation I told you needed to know. This is the equation that is on the license plate of a colleague of mine, without the beep. Entropy K log W. Okay? You need to know that. And this is the Boltzmann constant. Okay, the Boltzmann constant, named after Ludwig Boltzmann, who came up with this whole thing. Okay, and then killed himself because people didn't believe him. It's true. Look it up. Boltzmann with two M's. So this is just that Pascal's triangle thing, which I don't think I ever learned in high school. I saw it, but I never learned it. And this, once again, this is a way to figure out how many possibilities there are. Oh no, this is factorial stuff. Anyway, I couldn't get rid of this. I don't even want to show you this. Okay. This is important, that the entropy of the universe is equal to the system and the surroundings. Okay? A little bit different from what we learned before, where you only have two things. You got the surroundings and you got this. But in this case, the change in the entropy of the universe is equal to the delta, the entropy change of the system and of the universe. And it is always equal to 0 or greater than 0. It's not the other way. Okay? It's either equal to 0 or greater than 0. This is for the universe. Okay? This is the universe. It's hard for us to understand that, but it is true. So, if it is greater than 0, it is spontaneous and irreversible. And what do I mean by that? Spontaneous means it'll happen on its own. Doesn't mean, once again, I took the ball up the stairs. Was that in this classroom? Did I do it in this class? Okay, well, whatever. If I take a ball up there and I just give a little energy, I kick it down here, it comes all the way down, and that is a spontaneous reaction. Needs a little bit of a kick, but it goes. But it goes to completion, it ends up down, and it's never going back, okay, without me doing a lot of work. So that is a non-reversible reaction. So spontaneous and irreversible. Irreversible would be like if I took some paper and I burned it, and it makes CO2 and water vapor, and I can't now take water vapor and CO2 and make a piece of paper out of it. Okay. Plants can, but I can't make it reversible, okay? Instead, if I take a balloon and I squeeze it, I can actually make the volume smaller, right? Okay, if I had my drink a little bit more drank, I could just step on that 1/2 liter bottle, and I could make it so that the volume was, you know, maybe 350 cc's, depending on how heavy I am. Okay, I can make it smaller. Number of molecules doesn't change. I can actually make it smaller, and then I get off, and guess what? Back to normal. That's a reversible process. So for spontaneous, irreversible, entropy always gets bigger for the universe. If it's reversible and at equilibrium, and folks, there are fields. There's non-equilibrium thermodynamics. I mean, there's a lot of things that we have that if you're a chemistry major you will take. There's time-dependent quantum mechanics. There's time-independent quantum mechanics. There's classical mechanics. There's equilibrium, all kinds of stuff, okay? I suggest, because you're not going to learn from me, please go on, and I'm not that good at it. If you go on Wikipedia or something, or go on Google and type in examples of, you know, spontaneous reactions, examples of non-equilibrium reactions, whatever, you might actually read something that will help you, okay? On an exam, I will, for the most part, tell you if it's reversible or not. Although I've just told you that if I take 1 mole of methane and I burn it, that's not reversible. I can't now take that energy and just shove it back into the water and the CO2 that were made and do something to it to make it be methane again. Okay? So most of the time I will tell you if it's reversible and at equilibrium, but there are sometimes I don't have to tell you. And if this just doesn't happen. This doesn't happen. For the world, for the universe, it doesn't happen. It can happen in our little systems world, but it can't happen once again. Then we're talking about the delta S of the universe. All right, so look at this. And I'm not very good at explaining this either. But we've got 2 boxes, and in this case, the rules are you got to have 4 of whatever these are, ping pong balls, in one of the boxes. Okay? So you can only have it in this form here or here, right? So 4 balls right here. You got distribution, this is distribution 1, and you got this many microstates. Now in this case, let's say that we say, okay, we still got the same 4 balls. Yes?
So the values of the greater than, equal to, or less than 0, is that only for the
Never less than 0.
Yeah, is that only for the system of the universe?
That's only the universe.
Okay, so when we do like set...
You can have entropy changes that are negative.
Okay.
Yeah, absolutely, and that's the problem is that we're talking about the overall universe. We're talking about when everything is considered, entropy does not go down. Okay, that's because there's heat involved and all kinds of other things. Okay, but we're going to do a lot of calculations today for calculating entropy, and we're going to have some negative values. So absolutely, you can have it negative changes, but for the whole world, it never goes negative. So in this case, now we got 2 boxes, 4 balls, and we can actually arrange this 4 different ways. If the rules are you got to have 3 balls in one, you got 3 balls in one, and then you got 1, so you got 1, 2, 3, 4 that's outside. Okay? So we got 4 microstates. Now look at this one. Now that we say, okay, well, let's say we can have 2 in each one. So now we have 6 microstates, still same number of balls. Okay? So, would you say that the entropy is greater in this case or this case? Okay. The more microstates you can have, okay, the more combinations you can have, the higher the entropy. Okay? That SK log W, the W is this. Okay? Here the W is 4, here the W is 6. So right now, folks, get your calculators out, wake up. A lot of people sleeping right now, jeez. I want you to tell me, what is the change in entropy, or the ratio of the change in entropy, between going from this to this? I need somebody's buddy. Alright. Sorry, but you're my right hand man. Yeah, I am. So they're on my desk. They're on my desk. Yeah. So just get 2 or 3 from each bag, okay? Okay. Thank you, bud. I got it. You don't want to go right now, it's okay. I still got 1 more. Oh. If you want to hang out, but sometime I need you to go in the next 20 minutes, okay? Okay. Okay, what's the answer? What's the answer? How many of you don't have a clue? Okay. So, what did I say was the Boltzmann equation? S is equal to K log W. Okay? W, I said, was these. I said W of 4, W of 6. Right? So, what is the change when you go from here to here? There's several ways you can do this, folks. Okay, one way is just to say, well, what is W right here? U. What is W? 4. Okay. What's the log of 4? Do it. Do it. Log of 4 is what? 1.4. What's the log of 6? So what's the ratio of 1.8 over 1.4? About 1.4. What is it? 1.3? Okay. So this has 1.3 times more entropy. You don't need to know K. Why do you need to know K, right? It's a log. K doesn't change. So another way you could do it was just to be divided. Go S equals K log W over S equals K log W. Okay? And we're going to get to that. So do you understand it? W, folks, is the number of microstates. Okay? Now, so what was the answer? What is the difference in entropy between going from this to this? What did we say it was? 1.3. Okay? Now, what if instead we go from here to here? What is it? It's just the reciprocal of that, right? Okay, well, you're going to see where that's very important in a second. Oh, by the way, the notes are posted. Sorry. So, if the number of microstates final is greater, if 6 is greater than 4, then entropy is positive. If, however, we go from here to here, then it's negative. So we can have a negative entropy, okay? We're talking about this little system. We're not talking about the whole world, okay? We're going to do all kinds of, all day we're doing calculations about this. And it's all about calculating entropy. Everything we do today is to calculate entropy. Okay. I was kind of contemplating just getting rid of this, but this is just to show you got 8 balls and 2 things. The question is, how many different combinations? Each ball's got a different color, a different number, okay, so they're identifiable. How many different combinations do we have of getting 4 in here and 4 in here? Just, here are the answers. What do you think? Do you think there's 20 different combinations? Or 150? The point is there's kind of a lot. Even 20 is kind of a lot. Okay? Well, there are ways to calculate this. Once again, I don't deal in statistics. Here's the equation. And I heard people last night saying, oh, I feel like I'm back in high school math. Obviously, I never took that math class. So, N is the total number of things, and R is the number of things you need to choose from. So in this case, we can put 4 in a box, so that's the 4. So this is how you would use this, okay? Now, write that down. Okay, now everybody, you've written that down. I want to ask a question. No, I want everybody's eyes looking at me. Okay? Everybody looking at me. How many of you know what that exclamation point means? Raise your hand. Put them down. How many know where that button is on your calculator? Yeah, right. Okay, let me ask it differently. How many have never pushed that button on their calculator? So do this problem right now. How many don't know? Well, I'll tell you, because there's going to be someone. That just means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 8 factorial. Okay? That's what it means. Folks, if you do not practice these things, then when it comes to the exam, you're going to say, where the hell is that button? Your phone's got one? Jeez. I'll bet my phone doesn't. No. So how many have located their factorial button? How many have located it for the first time? Yeah, okay. It's good to know where that is. Somebody last night told me, yes?
It's not like in a factorial, it's like NCR, the permutation and combination.
Okay. She's asking even a fancier question. Okay. There's even like a button where you can punch in the R and the N.
Yeah.
I don't have that button. And if I do, maybe I do have that button, I just don't know where that button is. Okay? I may not let you use that button. I may make you write out what is 8 factorial? 4,000? 40,000. That's a big number. Okay, so maybe I'd make you write that. That way you can't use that button. So this is how you calculate it. And if you do this, you're 40,000. And then this is going to be 4 times 3 is 12 times 2 is 24. So it's going to be 24 times 24. Okay? The number comes out 70. Oh, geez, more of this. I don't understand this. I mean, I understand, I know Pascal's triangle. I could actually put in the next row if I wanted to, but I don't want to. Okay, now, we're going to have some class participation here, okay? This is like the Family Feud, okay, or The Price is Right or something, where I want you to shout out what is happening to entropy here. I want you to say increase or decrease as loud as you can. So I'm just telling you that. Now I'm going to go back. So now you see what the first question is. So you ready? Decrease. Could you just say it with just a little bit less enthusiasm? Decrease. That's a question, folks. Okay, so maybe we didn't learn supersaturation. So supersaturation is when you got a bunch of stuff in the solution more than you're supposed to have. All of a sudden you drop a little crystal in and boom, this huge crystal forms. So you go from like the liquid phase where it's all hydrated to a solid. What happens when you go from a liquid to a solid? Decrease. This game is not going well. You folks do not try to go on a game show. Oh, good. Anytime you heat up something, nothing else happens that has to change. If I heat this up, entropy goes up. Doesn't have to change the volume or anything. Okay? Heat something up, boom, entropy goes up. Subliming dry ice. So some folks don't know what sublimation is. I'm just going to tell you, that's when you skip the liquid phase. You literally go from the solid phase to the gas phase, and there's no liquid. What's that? So, right, it's going to go from something that's very ordered to a gas phase which is not ordered at all, and therefore we're going to see a big increase. Okay. Now we had an exam where there was a question asked about which of the following is not or are not state functions, right? How many remember that question? True or false? 2 points. How many of you think you got it right? How many of you think you got it wrong? How many of you don't have a clue? Okay. Well, what I didn't tell you, once again, I'm not good on telling you what a state function is. I got to really think about it, whether you know, temperature. How do I know temperature is a state function? I could sort of figure that out, but some of these things don't make sense, okay? But entropy, folks, is. And guess what? On an exam, guess how you can tell? We capitalize state functions. Oh, geez, that Q and W? Of course now I tell you. Now you're going to remember. If I'd have told you that the other day, you would see. Now you're going, gosh, if I'd have only known that. Actually, I didn't know it until last night. But actually, that's almost true. I didn't know it was maybe the truth. I figured it out on Wednesday a week ago. Okay, and then it was confirmed last night. Okay, so entropy, folks, is a state function. Notice it's got a big S, big H for enthalpy, E for energy, U for internal energy. They're all capitalized. And then you got a little W and a little Q. Okay? I'd like you to, even though I can't, I'd like you to be able to look at something and think about something and say, that's got to be a state function. Because it doesn't matter how I got there. Okay? So potential energy got to be, so energy has got to be a state function. Okay? But some of these other things I'm not so clear on. So what's your state functions? Don't care how you got there. So here's some standard enthalpy values, okay? This is just to show you. They had done calculations, and this is, so look at liquid water and gaseous water. Look at the difference. Almost a factor of 3. Makes sense. Okay? If you're in the liquid phase, you've got some randomness, but as soon as you get to the gas phase, you know, the world is your oyster, you know? So, and once again, this means the standard state. That means, folks, at 25 degrees C, that's just by definition. I wish it were not that. I wish it was like STP for PV equals nRT, but it's not. It's at 25 degrees C. Why? Because that's the world we live in. A lot of this was designed, okay, for that. Delta H we use because we're at constant pressure. Okay, constant pressure. So we just use delta H for that. So it's the world we live in is sort of how we define these rules. And then this would just be per mole. Okay, so if you have a mole of liquid water, its entropy is 70 joules per degree. Okay? So, question. Don has 10 moles of water, liquid water, at 25 degrees. He heats it to 26 degrees. What is the change in entropy? How many moles did I say? 10, okay. I meant to say 1, but so what is the answer? It's going to be 10 times that number, right? So look, I got joules per Kelvin per mole. So I've got 10 moles, so that if I have liquid water at 25 degrees, the entropy is 699 joules, okay? And now I heat it up by 1 degree. So the increase in entropy is 699 joules. Right? So anyway, you're going to have tables like this that are given to you. Okay, on the exam I'm going to be kind of mean, and I'm not going to give you, the 3 numbers you need. Okay, I want you to have to look for it. This is in the notes, you don't have to write it down. Yes? Really loud.
Because you're increasing by Celsius, when you have to convert that 1 degree Celsius.
No. Okay, so thank you. So her question is that, look, we got Celsius, we got Kelvin, well, how do we deal with this? Okay. So in every equation, folks, every chemical equation, you need to use Kelvin. Okay? But you don't need to use Kelvin if it's just a change, an incremental change. So this is more like a delta T. Okay? So delta T, I can say, okay, this is 298. 298K. Okay? If I'd have phrased it, you go from 298K to 299K. That's 1 degree Kelvin. That's the same as going from 25C to 26C. That's still 1 degree Kelvin. Kelvin and Celsius are the same thing. They're just offset by 273.15. Okay? So, but there's going to come a time today when you cannot just use that. So you remind me. Okay? When you see that equation, remind me that I said I was going to say something. Okay. So the first law of thermo just says that we can convert, we can't make energy, but we can convert it between different states, okay? We got heat, we got work. Energy can be converted from one form to another, but energy cannot be created or destroyed. That's the first law. Second law, the entropy of the universe increases in a spontaneous process and remains unchanged in equilibrium processes. So at equilibrium, anything that's at equilibrium, the entropy of the world doesn't change. So, this is just how you would say it in an equation. Okay? Equilibrium processes, change in entropy is 0. Spontaneous processes, change in entropy is greater than 0. Hey, Rafe, can you go get those throat things for me? Thanks. I only brought a couple of throat things today, so. Okay. And this is just a little picture. Some of you are more visual. Okay? That's the word I wanted. So this is temperature this way. This is entropy this way. All right? So I can start down here. Let's just say that's actually 0 degrees Kelvin. 0 degrees Kelvin. And then I warm up the solid ice. Okay. I start down here at 0 and I warm it up to, what is the melting point of ice in Kelvin? 273. Okay, so that's at 273. But I've been putting heat into it. Look at the temperature. So if I had a point right here on this and a point right there, and I said which one has more entropy, what would you say? This one, because the temperature is increasing. Okay, it gets to here, and then all of a sudden the temperature doesn't increase. I got to give it all this energy. Okay, I've got to give it energy because the entropy of fusion is increasing, and now it starts. This is now 0 degrees, so this is 273 or 0 degrees Celsius. Goes up to 100, and then it boils off, and then so on. Okay. So here you have the molecules that are far apart, and they're happy, and la-di-da. Here we have a liquid, so they can kind of float around. Here it's a solid. Now during this time here, folks, those water molecules can still move a little bit. They can't move around, but they can still sort of shake and wiggle and bend. Okay? Once they're liquid, you know, they can do this. Okay, they can slosh all around. S equals K log W. W of 1. What is the log of 1?
0.
Okay. Folks, you can save yourself all kinds of time on an exam by knowing that. Okay? I could give you temperature. I could give you all kinds of things. Okay? Some big hairy question. And somewhere in there I say, and there's one microstate. Answer's 0. You don't have to go through the whole thing. So, S equals K log W. When W equals 1, entropy equals 0. That means the entropy. Doesn't mean the change in entropy. That means the entropy. The entropy, the actual entropy of this solid ice right there, when you only have a W of equal to 1, once again, it's not when it's here or here or here. It's actually when it's right at absolute 0. At absolute 0, there's no movement of those molecules. W of 1. Okay? The bad news is you can't get there. That's the third law of thermodynamics. In the very beginning I told you that the three laws are, let me see. What was that first one? You can't, what was it? Okay, you can't break even. Second law is you can only break even at absolute 0, and the third law is you can't get to absolute 0. Okay? So this is where W equals 1 is right there. And we don't get there. So our world is, W is huge. Okay? Okay. Folks, products minus reactants, you must have balanced equations. So, this is, once again, this is at 1 atmosphere, so that little 0 up there means that this is at 1 atmosphere and 25 C. That's what that notation means, that the entropy, standard entropy is that we're at 1 atmosphere and 25 C. And then this is just the entropy of reaction. So we look at this equation right here. This is then what the proper way to write this would be, okay? That the change in entropy is products minus reactants. You need to have the coefficient C times this of C, D times this of D, and once again, the small ones are the coefficients, and this whole thing then is the equation for figuring out what the delta S of reaction is. Looks like that. Do this now. What's that?
Don't we have to know the entropy?
Okay, oh yeah, so all I'm asking you to do is to set it up. Sorry, yeah. Okay. I'm going to give the entropies in a second. I just want you to set it up in this format, okay, using this equation right here. So it should be pretty simple, folks, okay? Once again, it's not very complicated. You cannot forget your coefficients. Those coefficients, folks, okay. Now do it. How many didn't get this right? Okay, this is the thing you would write down, okay, on an exam. You would need to write this down. Once again, products, how many CO2s did we make? 2 moles. 2, so it's 2 times whatever the entropy of that is, minus how many moles of CO2, or CO? 2. How many moles of O2? Now, somebody asked last night, what you done? You said that when we did enthalpy, we didn't need to have oxygen in there because oxygen is free. True, oxygen is free, but oxygen has entropy. This is entropy, folks. This isn't enthalpy, okay? And so if you're changing the entropy of oxygen, we've got to count that in. So you do need to have the oxygen right here. How many got that answer? Good. If you did not get that answer, then figure out what you did wrong. Practice, 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 okay? I'm going to be very good this time about looking at the questions for the discussion that I will assign today that starts for tomorrow, okay? These discussion questions will go from tomorrow through next Thursday, and they're going to be just more of this stuff, okay? Okay, so this is just a visual, all right? If you've got a reversible process, the amount of the entropy going up and going down equals the opposite of each other, and the delta S of the universe is equal to 0. This is reversible. If I showed this picture, folks, I said which one of these is reversible, which one is not reversible, I would expect you to know that if the entropy, if these arrows are the same size but in opposite directions, that the entropy is 0. This is reversible at equilibrium. This one, look at this. We've got this much entropy that went up here, this much entropy decrease in the surroundings, and therefore you add these two up, there's a little bit extra this way, and so this has a delta S that is greater than 0, which would mean this is not at equilibrium and it is spontaneous. It's just a picture. Don't freak out, but that's how you would read this thing, okay? I believe this came from your book, so look at it. Here we have the same thing. We're at equilibrium. Look at this one. The entropy didn't change at all. In other words, there was no negative entropy for the surroundings. So this, in this case, the delta S is equal to the same for both of them. The entropy went up here, and instead of it going down like it did here, there was no change in entropy. So these arrows are the same size. Once again, This is a non-reversible process. I can't see putting something like this on the exam, folks. Okay? But I feel obligated to show you. Okay. Now, last night, just for the heck of it, I went on Google and I just typed in Rydberg constant or something like that. That's what the R is. And look at how many values there are. I didn't know there were that many. And actually, they ran off the page. So the one we had used for enthalpy is the top one, right? 8.314 joules per degree, and then it's per mole, okay? How many would see that number and say, okay, I'm okay with that? So that I'm familiar with that, okay? Now what I want you to do though, and look at this one right here. Everybody see this one right here? I've never seen it like this, okay? But I always learned 0.08205 liter atmospheres per degree mole. Look at this one, 82. Why is this 82? And I learned 0.082. That's right. Centimeters, not liters, Don. How many centimeters in a liter? Yeah, 1,000, folks. That was on the exam. 1,000, that's the definition. Okay, that's just the definition. 1,000 cc's, okay. In my soda here, I have 500 cc's. Don's soda has 500 cc's. How many liters? A half. I have 500 cc's, I have a half a liter. Okay, so this is perfectly fine. I could give you that on an exam, couldn't I? That'd be mean. But I could do it because sometimes I am mean. But look at this. What's amazing to me is look at all of them up here that have the 8.314. I was shocked. One. Now this is 8.314 ergs, whatever. But it's like you got to multiply it by, you know, 10 million. Okay, here's one, but look at this. Liter pascals per degree mole. That's exactly like that one. Oh, no, this is exactly like, well, anyway, never mind. But I kind of like was freaking out. I'm going, okay, well this is like a new revelation to me because I didn't realize there were so, look at this. 8.3, 8.3, 8.3, 8.3, 8.3, 8.3. Okay? Now some of them have, once again, they have different values here, but I was a little bit shocked. So, just so you know, a 8.314 liters kilopascals per degree mole. So, we're going to have to use that number, okay? I'm just showing you there's a lot of R's, and I was shocked. Okay, write this down. These are equations, these three equations, you're going to have to know on the exam. You don't have to memorize it. Well, I'd like you to know this. This will be given to you on the exam. Okay, so folks, yes?
Is there a reason why on the first two equations it's the second translate
It's the what now?
on the first two equations it's like T2 and then it's B2, but on the third equation it's T1?
Absolutely. Absolutely. I'm going to tell you right now. Okay, so I'll tell you in a second. So our folks, I showed you this before, it can be like about 15,000 different things, all right? This is the R we're usually going to use because it's energy, okay? Entropy's in joules, joules per degree. K, folks, the log K, you know, S equals log K, or S equals K log W. The K is the Boltzmann constant, and all that is just R divided by Avogadro's number. Okay, so this is what K is equal to, in case you want to actually figure out the actual entropy of something. But this will be given to you. Okay, I just wanted to show you where it comes from. Okay, so these are the three things you should write down. Okay, so let's look at the first one. Okay, change in entropy. Okay, let's do a problem where I say the change in temperature, we're going to use this one, the change in temperature goes from 200K to 300K. 200K to 300K. What is the change in entropy? What is the relative change in entropy? That's a better question. 300, you go from 200 to 300. What's the answer? Okay, this is a question you should do in 26 seconds. What was the question? Entropy, the temperature goes from 200 Kelvin to 300 Kelvin. What's the answer? How many don't know? How many do know? What's the answer? 0.405. Okay. Did anybody else get that answer? Okay. So, if you are not afraid of math, you would look at that and you'd say, oh, no, everything else cancels, okay? The entropy, delta SC, heat capacity, that doesn't change in going from 200 to 300. The only thing that changed was the T2 and the T1. So you're really looking at the log of 300 over 200, or the log of 3 over 2, or the log of 1.5. So all you should do is just punch in your calculator, log 1.5, and you get 0.4, right? Is that what you got? So it increased by 0.4. Okay, entropy went up. Now we know, folks, that temperature, what did we say temperature does to entropy? It increases. Okay? So this makes sense that as you increase something in temperature, that the entropy is going to be positive. Okay? What if instead I'd said you go from 300 to 200? What is the entropy? So what is the log of 2 over 3? Negative. Perfect. Because anything less than 1, log of 1 is 0. Log of anything smaller than 1 is a negative number. Negative number. That's what happens. The temperature decreases, entropy goes down. It's a negative. What I want you to do, folks, as I told you on about day 2, I want you to have the equations in your head, but I also want you to sort of physically see whether something makes sense or not. In this case, it makes sense. Increase in temperature, this value is going to be bigger than 1, therefore the entropy increases. Okay? Now, this lady right here, no, somebody, that lady, somebody asked me earlier, maybe it's you, okay. What about Celsius and Kelvin? So let's do that problem, okay? Let's say Dawn soda goes from, because it's warmed up since I've been here, okay? So it started off at about 5C, and now it's 20C. Okay. Use Celsius, don't use Kelvin. I just want to show you how screwed up you'd be. Okay? So if I say it started at 5 and now it's 20, you would put 20 here and 5 here, right? That would be the log of 4. That's a big number. What is the log of 4? 1.3? It's a big number. Compared to, now let's do it right. So it started at 273 plus 5. So it started at 278 and went to 298. What's the difference between the log of 4 and the log of 298 over 278? Huge. 298 over 278 is not a very big number. It's greater than 0, but it's not a very big number. So you absolutely, folks, cannot screw up. If I give you Celsius, you've got to add that 273. Otherwise, your answer is going to be way off. So what is the log of 4? What did we say it was? 1.4? Okay, and what is the log of 298 over 278? Holy smoke, we're off by like a factor of 100. Do not ever, ever, ever use Celsius. Now, if I'm talking about a change in temperature, and all I care about is the change, and the absolutes don't matter, then you can use Celsius, okay? All right, let's go on to this one. Volume. Okay, think about it. I've got my 0.5 liters here. When I finish it, if I step on it, yeah, I can even do this. Watch this, because I'm so strong. And this volume is smaller than this. When I squeeze it, as hard as I can, the volume goes from 0.5 liters to about 0.4 liters. Okay, well, maybe not about that much, but we'll say. So, would you expect the entropy in this to be smaller or larger? Smaller, right? The entropy went down because the volume that it had to run around in decreased. Okay? So look at this. If the volume is bigger in the final situation than it was initially, then this number is going to be bigger than this, which means that this number is going to be greater than 1. Log of 1 is 0. Log of 1.01 is not. It's a positive number. Okay? So this makes sense. Increase the volume and increase the entropy. Are you following me? Now this lady back somewhere in here said, hold on. All the other ones are V2 and T2 over T1 and V1. What, did you screw this up? So I had to make a decision. Okay? I would have preferred to put a negative there. Look at the pressure. Okay, same thing with this. What is the pressure on this thing right now? Let me open this up, close it. 1 atmosphere, right? A whole lot more than an atmosphere, trust me. I got a powerful grip, okay? So, what happens is I increase pressure. Volume goes down. So delta S has to go negative. So the only way we can make that happen, okay, is either to put a negative here, which I would have preferred, but your book doesn't. It just goes P1 over P2. So if you want to use a negative and then make this P2 over P1, I'm fine with that. Whatever works. Just don't screw it up on the exam. Probably because the person who's grading it probably is not going to know that. Okay? So once again, T2, V2, with P1. So these equations, folks, are equations you're going to need for the next set of things we go over. Here we go. Do this one. So entropy, folks, is the summation of several things. If the temperature changes, you got to worry about that in entropy. If the volume changes, you got to worry about that. Pressure changes, you got to worry about that. So in this case, we're going from 20 to 400, and we're going a volume from 20 to 5. So you just break it into two pieces, okay? Now, in those equations, folks, we always needed an n, right? We needed an n. We got nr, okay, log something. So sample nitrogen gas, this volume at 5 kilopascals is heated to this. So we have to figure out how many moles, okay? You can never go wrong figuring out how many moles something is. So this is not an easy question. I would prefer to start something with something easier, but this is what your book gave me. So it's two parts. So we're going to plug it into this. Now don't forget, the R, this R right here, is the same 8.314, and it was kilopascals liters per degree mole. Okay? That's why I gave you that. So I think, here we go. This is what you got to do. 5 kilopascals times 20 liters over 8.3. This is your R, and this is your temperature. You had to rearrange the equation because PV equals nRT. We needed N by itself. Okay, we needed N by itself. So we kept the pressure, the PV on one side, and brought on the other side the R and the T. Simple manipulation, folks, something you shouldn't be afraid of, okay? Or if this is scaring you or you don't understand it, then we need to do some remedial work in algebra. So now, folks, we know how many moles we have. Okay? So now we just have to plug it into those two equations, right? We change the pressure, and we change the, change the pressure, we change the volume, I think. Or no, we change the temperature and we change the volume. Okay. So we just need those two equations, and this is the N we're going to use in both of them. Okay? I'm going to move on. This is how you do the first one, okay? So the first one was where you have the delta S is equal to C log T2 over T1, and C is equal to, there's that N right there, and the heat capacity, okay? Heat capacity is right here, all right? I would have to give you that, okay? I have to give you that. You've had to figure this out, so it's just this times this, and then the log of a big number over a not so big number. So this is almost like the log of 2. So you plug this in, you get rid of moles, and you get joules per degree. This has no units to it, and you get a value of about 1 joule per degree. This is on the notes. Now we got a second part, right? We had a volume change. The good news is that we already know what N is. We know what R is, so all we have to do is plug those ones in there, okay? Went from 22 to 44. Oh, what's that? What do we know this is going to be the log of? The log of 2. 44 is twice as big as 22. Log of 2 is 0.6. Okay? So it's just going to be 0.6 times this thing here. Simple. But if you don't know the equations, not simple. So I have to give you the heat capacity. You have to calculate the moles. So folks, you can see where that PV equals nRT, it came in on the exam. It's something, I love PV equals nRT. You get lost? All right, so you just add the two together and you're good to go. Do this one. I'm nice enough to give you the moles here. So this is a very simple one. Boom, boom, boom. This is like a 4-point question on the exam. I mean, it literally should take you 1 minute. What's that?
The second one wasn't a continuation of the first
Oh,
one.
was it?
They were two different.
Yeah.
Oh.
Because there's a different number of moles.
Okay, well, they'll figure it out.
The first one was calculated, and the second one, it gave it in.
I didn't even notice. Okay, we've got an answer. This is just a little simple plug and chug, folks. Look at that. Thanks, buddy.
I have doors squeaks.
Oh, okay, thank you.
I just knocked my door. I was like, I'm ready.
Proud of you for thinking about that. All right, next. Do this one. Well, I can give you the answer for crying out loud. So it's 2 steps, folks, okay? Look at that. We have a change in volume and we got a change in temperature. So if you got 2 changes, you got to account for both. So you got to do the one where we have the T2 over T1, and then you got the other one that is the V2 over V1. So what's that?
You have to calculate them separately and then add them.
Do you have to calculate what? Okay. This is what you do for step 1. Just doing the volume first, okay? So once again, this, you got to have it in your brain, okay? But I was nice enough to give you 1 mole, okay? So does the answer make sense, folks? Our volume decreased from 5 to 1. What's the sign of entropy going to be? Negative. So this makes sense at least, okay? If you didn't get a negative value there, we'd have a problem. So for the step 1, the entropy for the volume change, folks, is minus 3.4. Now we have to do the second step, okay? And you don't know this. You can't do that without this information here, that the heat capacity is 12.47, okay? So it's moles times that, and then this. You're two getting ahead of me. I'm hoping that's what the next slide is. I hope. Yes?
On the test, are you going to have the specific, or the heat capacity?
Absolutely. I have to give you heat capacities. I have to give you that kind of stuff. Don't worry about that. I should have had this in the question, saying heat capacity is this. Okay, so very simple. Now, does it make sense? Does it make sense, folks? Sure, it makes sense. It got warmer. All you have to do is look at this and say, I know it's going to be a positive value. Now, did it change by much? 5 degrees. That's not much at all. So look at how small the number is. 0.2. It's almost a joke. You can almost forget to calculate entropy there, because what you do then is you add them together. Minus 13 plus this, minus 13.2. So entropy went up in one case and down in another, but the overall entropy was negative for that reaction. Okay? Now, you don't know what delta H of vaporization is for acetone. Okay? So you don't know what that is. Okay? But T sub B is the boiling point. There it is right there. Okay? So I will give you 2.9 times 10 to the 4th. Or in kilojoules, this is, water was 40.7, this is 29.1 kilojoules per mole, okay? Don't forget, look at that. We had to add that 56.2 to our 273.15. If we hadn't, we'd have wacky, wacky values. I'm going fast, but folks, it's on your notes, and it's in your book. Okay? This is not a bad chapter for books, okay? Now don't forget, folks, I could say that the entropy, oops, I guess I need to, if I said that the entropy of vaporization was equal to 88.3 joules per degree mole, the temperature change was, the temperature was 56.2 Celsius. What is the delta H of vaporization? All right? What I'm saying, folks, is that if I give you this and this, I could ask you to figure out what that is. It's a hint. It's a hint, folks. Okay, here we go. Write that down right now. So folks, this is an example of exactly what will be on your exam. Okay? Now first of all, you don't know what anything is up here. All you have is a balanced equation. So I will give you a table. Now you have everything you need. You just have to find it. I was so nice I even wrote it here. I'm in such a good mood. We have an answer? Is it too soon? Okay, I'll give you another minute. Okay, folks. Products minus reactants. What is the coefficient for the product? 2. What is the entropy, standard entropy of formation for ammonia? For a mole? 192. So you're going to multiply that value by 2. And then you're going to subtract N2, which is right here. You're going to subtract, so you're going to have a minus 191.6. And then hydrogen is a 130.7 multiplied by 3. You're going to subtract that off also. Okay? And you're going to get that. Coefficients 2 and 3 and 1, wherever 1 is. 2, 3. Oh, and 1 right there. And there's the value. You got to practice this, folks. Got to memorize those equations. All the other stuff will be given to you. Have a good weekend. I'll get those discussion questions out to you.